Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will apply the method of moment generating functions to find the probability distribution for a function of one random variable. Let's begin. So that is the problem that we are going to be solving together in this video. So we initially have a random variable z that is normally distributed with mean 0 and variance 1. So we have a standard normal. And what we're going to be doing is using the method of moment generating functions to find the probability distribution of a function of z, okay, a transformation, okay. But now, what's the idea behind the method of moment generating functions? The idea is to exploit the uniqueness property of MGFs. So what we're going to do is we're going to find the MGF of the function we are interested in, and then by the uniqueness property of MGFs, say that after we do our calculations we ended up with hey, this is the MGF of z squared is normal. That is not going to be the case, but I'm just trying to illustrate the idea behind the MGF method. So say that we ended up with the MGF of a normal, then by the uniqueness property of MGFs, the distribution of that transformation we're interested in must be normal. Okay? Okay, again, that is not going to be the case, but I'm just trying to illustrate the main idea. Okay? And the main idea is exploiting the uniqueness property of MGFs. In my opinion, this is the method of MGFs is the fastest method of the three that we have discussed. Okay, method of distribution functions, method of transformations, the method of moment generating functions. This one, in my opinion, is the fastest. It's the fastest, but there's a disadvantage to it. Disadvantage is that if after you compute your MGF, that MGF you end up with is not one that you're able to recognize, is not one of the most popular distributions, then you're back to square one. Okay, then you have to apply either the method of transformations or the method of distribution functions. On the other hand, this one here, the method of distribution functions, is the one that will always work, but is the slowest in my opinion. Okay? Okay, so here we go. Let's begin. So, as we said, main idea, let's compute the MGF of our function of interest. Okay, so in this case, it's just the square of a normal. As you can imagine, since we're going to be finding the MGF, we're going to start with the definition of MGF. Okay, so let me be very, very explicit about what we're trying to do here. We want the MGF of c squared, right? So the MGF of c squared by definition will be just the expected value of e to the power t z squared. Okay, just by definition. Okay, now we know that the expected value of a function of a continuous random variable is just the integral from negative infinity to infinity of that transformation of that function times the PDF. So now let me remind you that we're dealing with a normal 0, 1. So if you haven't memorized the PDF of normal 0, 1, you can refer to page 838 from our textbook. There you will find the most common probability distributions, both discrete and continuous. We want a normal with mean 0, so mu equals 0 and sigma is going to be 1. We have a standard normal. So in that case, the PDF will be 1 over the square root of 2 pi e to the negative 1/2 times, in this case will be z squared. Okay, so that's our PDF, and as we said, we would like to compute the expected value, and the support for a normal is from negative infinity to infinity. So we have this integral from negative infinity to infinity, and we need that PDF for a normal 0, 1 over square root of 2 pi, this guy here, e to the power negative negative z squared divided by 2 with respect to z. Okay, we're good, and this should be lowercase z. Okay, that's better. Makes sense? Just applying that theorem that we know about when we talked about expected values, right? Expected value of a function g, integral from negative infinity to infinity of g times the PDF. And in this case, that's the support for a normal from negative infinity to infinity. Okay, this PDF will be non-zero from negative infinity to infinity. Okay, so now let's try and simplify this. So this is the same as, let me use the linearity of integrals, and I'm going to factor out that constant. That's the first thing that I'm going to do, and then I'm going to combine these two terms, and the one that I am interested in preserving would be negative z squared divided by 2. Well, let me factor out negative z squared. Okay. So, I said I would like to combine these two guys, right? So this, right, is these two guys. It's the same as e to the negative z squared times 1 over 2, right? 1 over 2 minus, oops, I want that up here, right? Minus t, okay, that's what I want in the exponent. You guys agree? Negative c squared divided, well, times 1 over 2 gives me that term, minus times minus plus z squared times t. Okay, now that happens to be the same as just 1 minus 2 times t divided by 2, right? I'm just using 2 as a common denominator. That's it, right? Furthermore, what we can do is factor out that 1/2 so let me factor out that 1/2 and going to be using this one here. That's the same, right? Agreed? Okay. Now I want you to take a close look at this expression. Then you go, e to the negative z squared divided by 2 times something. That basically looks like a normal, right? We go back to our table and we go, a constant e negative 1 over 2 times something and then y squared. So basically this is, statisticians would call it, this looks like the kernel, right? So meaning that it looks like the PDF of a normal, except that we have there's a constant here missing, the constant that would make this guy legit normal, right? Okay, so if we do something like this, let this guy 1 over 2t be 1 over sigma squared, right? We're going to be doing a change of variables, if you will. So let 1 over a special sigma, the one that makes this guy a normal. Let me do it like this. So I'm going to be using sigma star squared to refer to the particular value that we have in this case. So if we let that quantity 1 minus 2 times t be 1 over sigma star squared, right? Then what we have is this. Right, and then we go, oh yeah, now it looks more like a normal, right? But we need that constant, right? Also note that if we set 1 over sigma star squared equal to 1 minus 2 times t, that implies that sigma star squared equals, you know, the reciprocal, right? 1 divided by 1 minus 2 times t. Well, yeah, 1 divided by 1 minus 2 times t. Make sense? Okay, so what we could do is just make this guy inside the integral a legit normal. How do we do that? Well, we just need this constant here, 1 over the square root of 2 pi times sigma, right? Okay, so that's exactly what we're going to be doing here. Let's include that constant, 1 over square root of 2 pi times our sigma star, right? Because it must be sigma, right? Okay. So times our sigma star but since we are multiplying, well, we are dividing by this constant, if we're going to be doing that and we don't want to affect things, right, we have to multiply by that same constant, and that would be multiplying by a1, and that's legit, that's legal, right? Okay, but now the thing is, what you have inside that integral is the PDF of a normal, right, with mean 0 and variance sigma star squared, and you're integrating from negative infinity to infinity. Since a normal is a legit random variable, the integral of its PDF from negative infinity to infinity is just 1. So this kind of a scary looking integral is just a 1. So we just have this times 1, okay? And then we can do a little bit of algebra. These guys will cancel out, so we only have sigma star squared, but guess what? That guy happens to be, right, the square root of this expression we have here. Let me rewrite that guy like this. This is the same as 1 minus 2 times t to the power minus 1/2. And that would be the MGF of z squared. So that's the first part of the method of moment generating functions. The next part is this. We have to be able to identify this as, you know, the MGF of something we have seen before. Okay, so what we could do in our case is we could refer to our table and see if we can find something that looks like that. Then we go, similar. Oh, -1. No. Oh, this one could work. 1 minus something times t to the power a different something. So in this case, beta would be equal to 2 and alpha would be equal to 1/2. So the MGF we ended up with is the MGF of gamma with parameters alpha equals 1/2 and beta equals 2. So let's say that. So note that the MGF of our transformation of interest, c squared, let me just write it down here. corresponds to the MGF of a gamma with parameters alpha equals 1/2 and beta equal to 2. Okay? Note something else. In this case, you can say that, right? And that would be fine, okay? And then by the uniqueness property of MGFs, Z square has a gamma distribution with parameters 1/2 and beta equals 2. But there's something more here. Take a look at the next one. 1 minus 2 times t to the power minus nu divided by 2. So this guy, right, happens to be, yeah, a member of the gamma distribution family, but we could be more specific. We know that chi-square distributions are particular cases of gamma distributions. So in this case, another possible answer would be z squared has a chi-square with 1 degree of freedom. Make sense? Or we could also say that z squared has a chi-square distribution with 1 degree of freedom. Let me find that chi-squared. Where do we have chi? There we are. Well, the letter that they use for degrees of freedom is nu, right? So, or we could also say that c squared has a chi-square distribution with 1 degree of freedom by the uniqueness property of MGFs. Okay? Make sense? So both answers would be acceptable. Okay? That z square has a gamma distribution with parameters alpha equals 1/2 and beta equals 2, or that by the uniqueness property of the MGFs, we could also say that this guy, z squared, has a chi-square distribution with 1 degree of freedom. Okay? Let's summarize what we did here. So what we did here is we applied the method of moment generating functions. And what we do in this method is basically exploiting the uniqueness property of MGFs. And the idea is this. What we just did, right, is finding the MGF of the transformation we're interested in, of the function we're interested in, and once we have it, we try and see if it corresponds to one of the ones we have seen before. If that's the case, we're done. If not, we have to try another one of our methods. Make sense? Okay, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.